Hello and welcome to G Fun Facts Online. Today we are diving deep into a topic that sounds like it belongs in a science fiction novel, but is actually happening right now in physics laboratories. We are talking about the taming of celestial fire. Specifically, we are going to explore how scientists are learning to guide high-voltage lightning bolts using nothing but sound waves. It is a story of how the vibration of matter can become the master of the flow of electricity. To understand why this is such a massive breakthrough, we have to look back at our relationship with lightning. Since the dawn of human consciousness, lightning has been a source of absolute primal fear. It was the weapon of Zeus, the hammer of Thor, a divine and unpredictable force that would split the heavens and strike the earth with total chaos. For thousands of years, we were passive observers. We hid in caves, we built temples, and eventually, thanks to Benjamin Franklin in 1752, we built lightning rods. But even Franklin's invention was just a suggestion to the lightning. It was a humble request for the bolt to take a path of least destruction. We were not controlling it. We were just giving it a slightly better option. For nearly 3 centuries after Franklin, that was it. We could attract a spark with a metal spike, but we could not truly guide it. And that is because an electric arc is inherently chaotic. It is a stochastic process. When a spark jumps, it is frantically searching for a path of least resistance through the air. This path is dictated by microscopic changes in air density, a speck of dust, or a slightly humid pocket of air. This is why lightning is jagged. It is a search algorithm running at a fraction of the speed of light, solving for the easiest route in real time. If a dust particle is on the right, it forks right. If the air is warmer on the left, it jags left. It is unpredictable. Now, in the late 20th century, we thought we found a way to control this using lasers. Scientists figured out that if you fire a high-intensity laser pulse, you can ionize the air, creating a filament of plasma. It is basically a conductive wire made of light. This actually works. In 2023, a team in Switzerland even guided atmospheric lightning with a massive laser on top of a mountain. But there is a problem. Lasers are brute force. They are the hammer of Thor approach. To do this, you need terawatt-class lasers that are dangerous, expensive, and rigid. You cannot easily bend a laser beam around a corner to guide a spark to a hidden target. It is a straight line or nothing. But recently, in the quiet corners of acoustic physics labs, a much more elegant revolution has been brewing. This is the era of acoustic lightning. Scientists have unlocked the ability to steer high-voltage arcs through the air with the precision of a conductor's baton. Using ultrasonic sound waves, we can now make electricity bend around obstacles, travel in predetermined curves, and strike targets with millimeter accuracy, all without a single laser beam or physical wire. So how does this work? How can sound, which is just moving air, control electricity, which is moving charge? To get it, we need to look at the anatomy of an electric arc. Air is normally an excellent insulator. The nitrogen and oxygen hold onto their electrons tightly. To get a spark, you need to break that insulation down. You apply a high voltage, creating an intense electric field. When that field gets strong enough, roughly 30 kilovolts per centimeter, it rips electrons loose and starts an avalanche called impact ionization. This creates a channel of plasma. But remember, the arc follows the path of least resistance, and the key variable that determines that resistance is air density. This is governed by Paston's law. Simply put, if you lower the density of the air, you lower the electrical resistance. Electricity loves to travel through low-density air. This is where sound comes in. Sound waves are pressure waves. They are oscillations of high and low density. If you could use sound to manipulate the density of air in a specific pattern, you could create a low-density tunnel that electricity would prefer to travel through. But a normal sound wave isn't strong enough. The breakthrough came when researchers like Dr. Azir Marzo and his team realized they didn't need the sound to create the vacuum tunnel from scratch. They could use the sound to guide the hot air created by the spark itself. Here is the mechanism, and it is fascinating. When a spark happens, it heats the air to thousands of degrees. Hot air expands and becomes less dense. This means the residual heat from a spark creates a lingering path of low resistance for the next spark. In a rapid stream of sparks, like from a Tesla coil, they want to follow each other. But usually that hot air floats up because of buoyancy, or twists around due to turbulence. That is why a continuous arc looks like a wiggling flame. The acoustic system intervenes here. Using an array of ultrasonic speakers, scientists create a standing wave. This is a sound field that stays in place. Inside this field, there are nodes, which are quiet spots, and antinodes, which are loud spots. Crucially, there is a force called the acoustic radiation force. This force pushes on particles or fluids that have a different density than the surroundings. Since the spark channel is hot and light, the sound waves push it. The acoustic field grabs this hot, light air and traps it. It holds the hot air in a straight line, or a curve, preventing it from floating away. So the next spark in the sequence sees this perfectly held tube of hot, low-density air and zips right through it. It is a self-reinforcing cycle. Spark heats air, sound traps hot air, next spark follows the trap. The result is a virtual wire made of nothing but organized sound and heat. To the naked eye, the jagged, chaotic spark suddenly snaps into a perfectly straight line, or a smooth arc, following the invisible acoustic beam. The machinery to do this is surprisingly accessible. You don't need a $1 million laser. You need a phased array transducer. These are essentially grids of ultrasound speakers, similar to parking sensors on a car. By carefully timing when each speaker fires, a technique called beamforming, scientists can sculpt the sound. They can create Bessel beams, which are long, non-diffracting beams perfect for straight lines. They can even create vortex beams. By spiraling the timing of the speakers, they create a tornado-like sound field. This vortex beam has a quiet core surrounded by a high-intensity ring, which is amazing for stabilizing thicker plasma channels. Perhaps the most stunning part is that they can bend the arc. In experiments, researchers placed a solid plastic obstacle between the electrode and the target. Normally, the spark would hit the plastic or jump wildly around it. But with ultrasound, they generated a curved acoustic field, an airy beam, that went around the object. The hot air channel was steered around the barrier, and the electric arc followed it perfectly, glowing like a neon tube bent in mid-air, but with no glass to contain it. They can even split the arc. By using multiple focal points, a single discharge can be bifurcated into a Y shape, striking two different targets at the same time. This is effectively a gas-phase electrical switch. Now, beyond just looking incredibly cool, this has real applications. Imagine high-voltage switches that have no moving parts and never touch. You could redirect massive currents just by changing a sound file. In manufacturing, we use electric discharge machining to cut hard metals. Acoustic guiding could allow for air-based machining, where sparks are drilled into a surface from a distance with micron precision. In medicine, cold plasma is used to sterilize wounds. Acoustic guiding could allow doctors to direct that plasma to a specific spot on a patient without the risk of a stray spark hitting healthy tissue. And of course, there is entertainment. Imagine a holographic display made not of light, but of floating fire, tracing animations in the air. Now you might be wondering, can we use this to guide actual lightning from a storm? Can we protect airports? Currently, the answer is no. Sound has limits. High-frequency ultrasound gets absorbed by the air very quickly. It loses half its energy every few meters. To reach a cloud a kilometer up, you would need impossibly loud speakers. Also, wind is a problem. A 20-mile-per-hour crosswind would blow the acoustic channel away, breaking the wire. Light from a laser doesn't care about wind, but sound does. However, for industrial applications and laboratory physics, this is a game-changer. We are currently at the Franklin kite stage of this technology. We have proven it works. Future research is looking at hybrid systems, maybe using a small laser to start the path and sound to stabilize it. We are also looking at using those vortex beams to spin the plasma, making it even more stable. In conclusion, acoustic lightning represents a paradigm shift. For a century, we thought the only way to control electricity was with heavy shielding or brute force. We fought force with force. This approach teaches us a different lesson. It shows us that the most chaotic forces in nature can be tamed by shaping the environment they inhabit. By whispering to the air with ultrasound, we create a path of least resistance. The lightning follows, not because it is forced, but because it is the easiest way forward. In the hum of the ultrasonic array, we have found a new kind of conductor, one that wields an invisible baton to direct nature's most volatile orchestra.